However, he was being spiritually inclined. He joined the Ramakrishna Mutt as a renunciate upon being impressed by the life and work of the Vedantic philosopher Ramakrishna Paramahamsa. His initial name was Brahmachari Brahma Chaitanya. He was renamed as Swami Vidyanathananda after receiving his saffron robe in 2008. Swami Vidyanathananda is a monk at the Order's headquarters in Belur Mutt. He was Professor of Mathematics and Dean of Research at the Ramakrishna Mission Vivekananda University till 2015. He is currently a Professor of Mathematics at Tata Institute of Fundamental Research, Mumbai. He has widely published and presented his research in the area of hyperbolic manifolds and ending lamination spaces. His most notable work is the proof of existence of Cannon-Thurston maps. This led to the resolution of the conjecture that connected limit sets of finitely generated Kleinian groups are locally connected. He is also the author of a book titled Maps on Boundaries of Hyperbolic Metric Spaces. And add that Professor Mahan also received the prestigious Infosys Award last year. Professor Mahan.
Yeah. So now it's technology, and I have no say. It's stuck, so I'll start as soon as the technology gets in shape. Okay. Okay, thanks a lot. Thanks very much. Okay, so yeah. Okay, so I'll try to begin an answer to this question, which is the topic of my talk, and I'll assume that everybody here knows calculus, minimal amount, but that's about it. And there are two problems in mathematics which have a fairly longish history. One is, sort of from the beginning of mathematics, there have been sort of two directions, one involving numbers, one involving shapes. So numbers have given rise to number theory, algebra, etc., etc. The other side has given rise to geometry, topology, some amount of analysis, and so on. So both these questions occupied some of the greatest mathematical minds for, any guesses? Couple of thousand years actually. So there are two very specific problems, and they were solved by two of the greats. One was Galois, the other was Gauss. And Gauss solved the geometric problem, Galois solved the algebraic problem. And being a geometer, of course, my personal bias, prejudice is towards geometry, so I'll answer the geometric problem. And that was this. I mean, of course, nobody knew what hyperbolic geometry was in Euclid's time, but the problem was posed by Euclid. Okay, so when we start off doing geometry in school, at the very inception, we are introduced to Euclidean geometry, first introduction to formal reasoning, and we are given a bunch of axioms. Yeah. Euclid's axioms. So there's a whole collection of them, but this is a sort of a very short summary of the axioms of Euclidean axioms in two-dimensional plane Euclidean geometry. Since the previous talk was largely a life science talk, I can't resist making this statement. Apparently, the part of the human brain that is involved in asking apparently childish or meaningless mathematical questions, which very often lead to profound things, is exactly the part of our, well, has a sizable overlap with the part of the brain that imbibes very new information as a child. Child meaning, say, within the first 2 or 3 months. So asking these meaningless questions, apparently meaningless questions, is definitely something that helps us acquire a lot of knowledge, and some of our profoundest questions come from here. So I'll try to see. I mean, so Euclid was exercising presumably that part of his brain, and he posed a question. Yeah. So he laid out axioms. So I'll just summarize the axioms first, and then get to the question. So the first of Euclid's axioms, there are 4 axioms, and then there's a 5th postulate. So 4 axioms. First one says that given any 2 points in the plane, you can join them by a straight line. So this is what we in today's terminology we would call a straight line segment. Yeah. The second says that if you have a straight line segment, you can extend it infinitely in both directions. Yeah. So that by infinite extended object is really what we call a straight line. The first object is what we will call a straight line segment. Third axiom says that given any point on the plane in the radius, you can draw a circle. Fourth axiom says that all right angles are equal to one another. What does that mean? It means that all other angles are wrong angles. But what? Yeah. So I mean, what exactly does that mean? I mean, what is a right angle? How would you define a right angle? Yeah. So you take a straight line. So already you have a notion of a straight line given by the first and second axioms. How would you define? So basically, you take that straight line, take an arbitrary point on it, and so now you have a canonical angle. There's an angle coming from minus infinity to that point and then going off to plus infinity, right? Bisect that angle, that's a right angle, okay, by definition. Okay? What the fourth axiom says is that angle that you got is independent of the line you chose and the point on it that you chose, right? So that's the formal content of this. Okay, before I come to the fifth postulate, let's look at these four axioms a little more carefully. And what these axioms are really doing is that they are defining the players of the game. Yeah? What are the objects that we are going to play with in order to build up our geometry? The first axiom defines for you a line segment in terms of what? So what are the things that are sort of going there, have been quietly shoved under the carpet? There's a plane and there are points on it. Yeah. So these are things that we don't define. Yeah. But with that data, we are going to define the players of our game. Given any 2 points, you are able to define a line segment. That's what the first axiom does for you. Yeah. So all these four axioms are in some sense defining players. Yeah. Second defines a bi-infinite line segment. Yeah. Bi-infinite straight line. Yeah. Third one defines a circle. So a circle has a center and a radius. That defines the circle completely. Yeah. And the last axiom defines the notion of an angle. Now let's come to, so these are in some sense definition axioms. First four. The fifth guy is different. It's a different status. What does it say? It says that you take two straight lines, assume these are straight, and now you let them fall on a particular line, and suppose that the sum of these two angles is less than 180 degrees. What that axiom says is that then these two lines, if they are extended in this direction, they are going to intersect. Yeah. This was the original formulation of the fifth postulate. Yeah. There's a crucial thing here. If these two is less than 180 degrees, it's going to meet on this side. By the same axiom, if it's less than 180 degrees on the other side, it's going to meet on that side. Yeah? What if it's exactly equal to 180 degrees? So then we have no idea, right? So the two lines don't know which side to meet, so they don't meet. That's not a proof, but essentially you can crank it up to a proof, and that reformulation that the lines do not meet is called, that's really called the parallel postulate. So the fifth postulate is equivalent to saying that through a point, so do not meet gets a special name, they are called parallel, and this is what it says. You have your straight line, you have a point outside it, there's exactly one line through this point on the plane which does not meet this line. Basically, from here you draw any line, take this angle, make an angle such that the sum is 180 degrees, and then that line will not meet. Okay. So the fifth postulate says that through a point not on a straight line, there is one and only one straight line to the point parallel to the given line. This formulation of the of the fifth postulate is called the parallel postulate. Maybe later as I say. Now, what was the problem that Euclid posed around 200 BC or earlier? Prove the fifth postulate from the remaining four postulates. This was his problem. If he was, yeah, I mean, I'm not sure, I mean, I have not read the original, but I guess in hindsight, the problem should have been posed as, can one prove the fifth postulate from the remaining four postulates? Okay? Right. The sort of inside this question, there's a kernel of perhaps the deepest theorem of mathematical logic in the 20th century lurking. Okay. So yeah, 200 BC, 20th century. See the gamut. All right. So now let's, before we get on to the maths, let's yeah, it's a little bit of story time. So what's the history of the problem? Zillions of people worked on it. Finally, it was cracked by Gauss. Started thinking about parallel lines in 1792. In 1824, he wrote to a friend. Taurinus was a friend. He writes, the assumption that the sum of three angles of a triangle is smaller than two right angles leads to a geometry which is quite different from our geometry. At that point of time, our geometry meant Euclidean geometry, but which is itself completely consistent. So the sum of the angles of a triangle, three angles of a triangle, is equal to 2 pi. That's also equivalent to the parallel postulate. So basically, you look at a triangle, draw a line through here, this angle is equal to this angle, this is equal to this, so the sum of the three angles is 180 degrees. And from that you can go back to the parallel postulate. Alright. So there's a little bit of mathematical gossip, perhaps apocryphal. Gauss did not publish this work. And there's sort of questions as to why he did not publish this work. And there's a sort of a slightly naughty explanation given. By 1824, Gauss was an established mathematician and he did not want to appear wrong in public. There's some reason that is given, perhaps not. However, Gauss is not, so basically the discovery of this, this geometry where the sum of angles is less than 180 degrees is not in popular literature attributed to Gauss. Which is, so who are they attributed to? People who published it first. But before they published, and there's some other history. So you know of these hyperbolic functions, hyperbolic trigonometric functions. Cosine hyperbolic e power x plus e power minus x by 2. Sine hyperbolic e power x minus e power minus x by 2, etc., etc. So these functions came in trying to compute areas and other mensuration problems of before Gauss. So in the 18th century, some of these things were actually computed by Lambert. And again, after that, the discovery was made simultaneously by two people, a Hungarian mathematician by the name of Bolyai and a Russian mathematician by the name of Lobachevsky. Lobachevsky's book is completely unreadable. It's, yeah, because it's got all this sort of, it's, apparently somebody, I think Gauss really went through that. Basically, in order to understand Lobachevsky's work, it's extremely computation intensive, very technical, and in order to understand what he is trying to say in 500 pages, you have to read all 500 pages. So there's no way you can sort of get the crucial idea. I mean, if you, I mean, people who do maths research sort of, well, okay, let's get the main idea, then we'll try to work out the details. You can't do that. Yeah? You have to go through every tree individually in order to understand the parts. That's sort of style that Lobachevsky adopted. Well, as good or as bad as any other, I guess. Anyway, So he published his paper on the principles of geometry in 1829-30, and a couple of years later, Absolute Science of Space was published by Boyer, which is much more intuitive. Anyway, at this point of time, what were they trying to do? They were trying to formulate a geometry in which the fifth postulate would be violated. Which means what? Which means that, okay, reformulation of the parallel postulate, sum of the angles of a triangle is 180 degrees. So they were replacing it by the axiom that the sum of the angles of a triangle is strictly less than 180 degrees in a triangle. Yeah? That's what they were doing. And then they were trying to build up a geometry. So less than 180 degrees has nothing to do with hyperbola. So the term hyperbolic geometry came much later, when hyperbolic geometry was really put into a certain context. And I mean, in hindsight, it's a wonder that it was not discovered earlier, because almost all geometries, in a certain fairly precise sense, are actually hyperbolic. This Euclidean geometry is some exceptional thing, yeah? And it is only this sort of perverse habit that we have grown into that tells us to think that this Euclidean geometry is the natural thing and hyperbolic geometry is not. Okay, so I'll try to, I'll try to justify that so that it's not just a sales pitch, but it's mathematically accurate. Okay, so it was formulated by, the word was coined by Felix Klein, but the person who really brought it into mainstream mathematics and tied it up with zillions of other areas is Poincaré. Around, just after Klein. Klein had an ongoing competition, one side, from his side only, as he was always doing, with Poincaré. And, anyway, so, I think what happened was that he was trying to discover certain groups. Poincaré found them out, and he called them Fuchsian groups. Klein was very annoyed. He said Fuchs had nothing to do with them, which is perfectly true. And then, so then I think Poincaré went up one more dimension. These were two-dimensional objects. He went up one more dimension, discovered some groups in 3 dimensions. He said, okay, I'll call them Kleinian groups. So Klein had nothing to do with Kleinian groups. Fuchs had nothing to do with Fuchsian groups. Poincaré had everything to do with both. So anyway, so this tying up various things, things which are even today, applicable in number theory, things called modular forms. All of it, has origins there. Yeah, this certainly geometry, certainly topology, but also things which look far like number theory. All right. So now let's get back to the mathematics from the gossip, and let's restate the parallel postulate in terms which are more precise. So what is the parallel postulate? It says that given a straight line, L, name them now, but crucially we define the context in a plane P, in a flat Euclidean plane P. See, if you define two straight lines as parallel if they don't meet, then in 3-dimensional space you have infinitely many lines, right? So you have one line running on this flat on the floor, you take this point on the top, you take a straight line and you just rotate it in a plane parallel to that line. You're going to get infinitely many lines, right? So you're talking about 2-dimensional flat plane Euclidean geometry. So that has to be said in a plane P. And a point X on P outside L, there exists a unique L prime lying on P, passing through X and not meeting L. Okay? Which we call parallelism. And now Euclid's problem becomes prove the parallel postulate from other axioms of Euclidean geometry. Good. The thing is, note, this is how a lot of mathematics is really done. There's a problem that is posed, and there is an unstated assumption which is obvious to everybody, but we don't spell it out. So Euclidean geometry was the problem was being posed in the context of Euclidean geometry, which means what? All of it is being done in a plane P. Yeah, everybody knows it. You spell it out. Yeah? And then you really start understanding, once you spelled it out, you understand that really this unstated assumption is the only place where you can attack the problem. So if you've not stated it out, if you've not exposed the vulnerable part of the problem, there is no point of attack. And so the reason it took 2000 years is that a large part of the time went in trying to understand what is the point of attack. There were sort of several things. Apparently this poet, Omar Khayyam, he attempted this problem for a long time. An astronomer, mathematician, he attempted this problem. Bunch of others. Yeah, it's sort of a who's who. You go through the history of this problem, it's, yeah, I think Jacobi, I've forgotten the list, and there's a very impressive list of mathematicians who attempted this problem. Okay, so basically, once you stated the assumption, stated the unstated, the common assumption, the basic question that we need to ask now is what is the context of the problem? So that means the problem is deep. This unstated assumption, which is really at the background of this entire problem, is the place where we need to attack it. So the question is, what is a pin? That which was undefined, so points on it, etc., etc. We don't know what it is. It's some axiomatic thing. It's a piece of paper. That's not a definition. So what is a plane? That was the question. We don't know the context. Basically the question was asked because there was a common shared context, but it was not formally clear. It was not something you could manipulate. You could manipulate the flares, you could manipulate lines, angles, circles, etc., etc., etc. But you were not allowed to manipulate the underlying structure, which is the plane P. So what exactly is the plane P? Can we understand it in some more fundamental terms so that we can manipulate it? That was the question. That's one of the main reasons why this problem took such a long time. And the answer to this question is actually comes from a very different area of mathematics. That's why it took a long time. And once we have defined that plane P, just note that in the Euclid axioms you have this line segment, and then the straight line is defined in terms of that, angle is defined in terms of that, right? So what we would like to do ideally is start off with a notion of a plane P. From that, derive the notion of a straight line. So a straight line now becomes an emergent mathematical object. Yeah? Not something intrinsic, not something defined, yeah? But something that emerges from the definition of a plane P as an object which has some characteristic properties. Yeah? So that is our goal. That is the goal of these three questions. And then notion of parallelism. Once you have a notion of straight line, the notion of parallelism is clear. Two straight lines are parallel, they do not meet. It's just a word. Yeah? So basically what we'd like is an a priori definition of a plane, and then from that define what straight lines are. Okay, good. So the answer for Euclidean geometry is R2 equipped with a certain metric. Metric means a way of measuring distances. What is that? It's ds square equal to dx square plus dy square. What is this? This is just an infinitesimal way of saying what the Pythagoras theorem is. A square plus b square equal to c square. Yeah. But if a is very small and b is very small and you want to sum, this is the only place where I'll need calculus. Okay. So basically, there's this infinitesimal way of using the Pythagoras theorem, and it's packaged in this one neat formula. What's the meaning of this formula? There's something infinitesimally small, its square equal to sum of two other infinitesimal squares, apart from some vague philosophical content. How are we going to translate that into maths? Yeah? So, if you open that package, and that's a formula, it's a package, yeah. What does it signify? It means that if you have a smooth curve on a plane, yeah, R2, then the length of that curve can be calculated, and this is where integral calculus or differential calculus comes in. This is computed by the standard formula that we know from high school, that integral of ds is, well, you parameterize your curve x of t, y of t, take the derivative x prime t, y prime t, and then you look at x prime t square plus y prime t square. So basically at every point you are looking at the two derivatives you're applying Pythagoras, that is giving rise to a certain length of a tangent vector at that point. And then you're multiplying it by dt, so that's the infinitesimal amount that you're traveling along the curve. Then you sum over t. So basically behind all this there is a fairly sophisticated amount of thinking that has gone on. Calculus came 1500 years, or 1580, so maybe basically 17 plus. Yeah. So yeah, maybe some 1700 years already of that 2000 years has been captured. Yeah. So basically, in order to manipulate the plane, we want something, some more fundamental structure. Yeah. So this structure came with Newton, with Leibniz, much later, 1400 something or the other. And there's a fundamental advance. I mean, we start doing our calculus in maybe class 11 or so, but we don't realize that today it's become part and parcel of our, of our toolkit. But it was not there before that, so people were not able to solve this Euclidean geometry problem. Yeah. Before that, basically because there was no more fundamental module. Yeah. Okay, so how many people are familiar with this thing, with this formula A on the board? Very good, enough. Okay, so that means I can carry on with it. Good. So this is the length of this curve, and then what's going on behind this is that you use some parameterization of the curve. Now, if you are given this formula for, if you define a Euclidean plane this way, do straight lines have a certain property, have a certain special property? Yes? Students? Yeah? With respect to this distance? Yeah. Go ahead. Guess. Come up with whatever answers you know. You think, yeah, go ahead.
So the ratio of dy and dx is constant.
Ratio of dy and dx is constant. Okay, but I have given you just this one formula, ds square. Where is dy dx? Yeah?
The length of path is minimum.
The length of path is minimum. Very good. So in terms of this L of sigma, the straight line is the unique kind which minimizes distances between points. Yeah? Alright. Where length is some object calculated according to this formula. Fine. So now we have, once you have this formula, yeah, once you have a way of computing lengths, shortest lengths are exactly what defines straight lines. So now the straight line has become an emergent object, right? It is defined in terms of this metric, in terms of the plane with the metric. It's no longer an a priori thing which you have to introduce as an axiom. Good. Let's proceed. So the straight line is the shortest distance as per the previous formula between them. And parallelism now is just as before. Two bi-infinite straight lines are parallel if they don't meet. Good. So now the whole thing boils down to what is a plane P. Now if you have a plane P with that formula, yeah, you can prove that two parallel lines, that there is one and only one line parallel to the first one. So if you take, so what does it mean? If you take your definition of a plane which was not stated in Euclid's axiom to be R2 equipped with that metric, then the parallel postulate does hold, right? Which means in order to address the question, can you prove the fifth postulate from the remaining four axioms, what will you have to do? This is basically trying to expose the point where you can attack the problem. It means you'll have to go back to that formula, ds square equal to dx square plus dy square, and modify that. With that formula, the fifth postulate will have to hold, right? So if you want to have a hope of saying that no, what you want to do, you want to change that formula, see that the first four axioms are satisfied and the fifth axiom is violated. And if you want to prove it from those, then what you'll have to do is that for all possible formulae that you put in here, that satisfy the first 4 axioms, the 5th axiom is also satisfied. So now the point of attack is well defined. Yeah. So we'll have to manipulate this one simple looking formula. So this is the question. So we'll have to, so basically, I mean, this is really okay. So hindsight is 2020. I mean, the person who really brought in this perspective was somebody in whose second thesis examination for the Habilitation. Gauss was the examiner. Bernhard Riemann. So that's how this yeah. Yeah, I have stories to say about that maybe if we have time later. Okay, so let's try to modify that formula. So how do we modify it? Take some subset of R2, and now instead of, so basically, okay, so the other thing to notice is that we wrote dx square plus dy square. Again, there was something that was unstated. The coefficient of that dx square is 1. Yeah? We did not write 1. Oh, everybody understands it's 1, right? So because everybody understands, nobody writes it. And 1 not treated as a constant, but 1 treated as a constant function over all of R2. So basically, understanding what is unstated in the problem is what probing this problem is about. Yeah? So what do? You replace, that's where you can hit the problem. So you replace 1 as a function over all of R2 by arbitrary functions now. Say f of xy plus g of xy. So now what is the general geometry? ds square equal to f of xy dx square plus g of xy dy square. What is happening? F and g are positive, and the length is computed according to the formula. You again parameterize x of t, y of t, x prime t square plus y prime t square times, earlier it was 1, 1. Now you replace the first one by f, the second one by g. Okay? And now you again have this is your generalization of that previous formula. Now, the problem from having absolutely nowhere to attack now is given you a huge amount of choice. All positive smooth functions f, all positive smooth functions g. How are you going to try it out for all f and all g? So there are sort of two basic things that go on in mathematics. One is you want to take a problem and work very hard once you know that there is and find some point of attack. That's what this discovery of this theory of calculus gave us. Once that calculus was discovered, now there's some huge amount of choice. Now you want to find one particular metric and test it out for them. But now it's like hunting for a needle in a haystack with cardinality 2 power c. Right? So, I mean, what is the collection? I mean, the cardinality of the collection of functions. That's a huge thing. Real line has cardinality c, right? And you want to choose one metric out of these. Yeah? So now it's basically really a rags to riches story. There was no technique available prior to calculus. Now you have so many metrics available, you don't know which one to choose. So the motivation to choose, so there are two. So the second step, I mean, this is the previous thing only accounted for some 1700 years or maybe something like that. The next thing, choosing the right metric, has to come from again some kind of motivation. Yeah? You have to have some clue, some intuition that okay, if you look in this direction, maybe you're going to get a metric which is going to give you something, some new interesting kind of geometry, and then you have to exercise that part of the time. So, before we get into that, so the notion of a straight line in this metric is replaced by a notion of a geodesic. So it's a path which minimizes the distances, but according to this revised formula. And all our congruences that we studied in high school, angle, side, SSS, side, angle, side, etc., all of those are examples of what are called isometries. So what's an isometry in this context? It's something that preserves that infinitesimal form of the formula. It preserves, therefore, if you preserve distances in the infinitesimal level, then you integrate out something, then the lengths of paths will be the same, right? So an isometry is something that preserves the infinitesimal form, hence preserves all lengths, hence preserves minimum length. Yeah, hence preserves the distance that we started off from in Euclidean geometry. Good. So we have these two notions. So what are these? An isometry is a map which means that you take xy going to x1, y1 under this map I. Infinitesimal thing for satisfied means you take f of x, y, dx square plus g x, y, dy square, that was the first ds square. And after you've transformed, it's x1, y1, dx1 square plus x1, y1, g of x1, y1, dy1 square. These two infinitesimal lengths must be the same. So an isometry, if you now you just set it down into a formula which need not have any other interpretation except calculus. That's something that you can manipulate. So this is what an isometry is. Good. Now, so the first part of the talk, I think we have been able to say that okay, why were mathematicians stuck? Because Riemannian geometry was not there. But then we'll have to choose a particular f, particular g. Yeah. Simplifying assumption, at least choose f equal to g. Mathematicians always try to find first a simple thing. If it works, then why should we complicate our lives unnecessarily? So choose f equal to g, for instance. Okay, even then, even once you realize there's one function f, smooth positive function, there's so many other. So how are we going to choose it? That choice was guided by something else in a completely different part of mathematics. This is what that Poincaré-Klein story was about. And that's the exposition that I'll be taking. You choose the Euclidean plane, but not all of it. You choose the upper half plane, yeah, y greater than 0. And equip it with a certain metric where you take the Euclidean metric and scale it by 1 by y square. Yeah. So f of xy equal to g of xy equal to 1 by y square, and you're taking y greater than 0. Why have I made this particular choice? Well, the short answer is because Poincaré tells us to do it. But why did, so the question is, why did Poincaré come up with this formula? That's a completely different story. Comes from a different part of mathematics which will define, could be the topic of a completely different talk. So I won't tell you. So there is a little bit of a rabbit out of a hat here. So from this uncountable collection, we picked out one metric. So once you are given, now let's try to compute what the straight lines are in this geometry. Yeah? And then we'll find out whether the first four axioms of Euclid are satisfied in this geometry and whether the fifth postulate is also satisfied or not. And then we'll have an answer to Euclid's question. Okay? So the first thing is, now you have this one simple formula to manipulate with. First theorem says that vertical straight lines. So what is the space you're looking at? The space you're looking at is xy. So this is y-axis, the x-axis. H is the upper half plane. Yeah, that's called the hyperbolic plane for a certain reason. And now you're computing. So you want to prove that any vertical line, is a geodesic, which means what? Which means you take any 2 points here. So that's x0, y1 and x0, y2, and you take any path between them. Yeah? You want to show that the length of this path calculated according to this new formula is less than equal to the length of any other path, sigma. So you parameterize sigma as sigma of t is x of t, y of t. Okay? So what is L of sigma? So sigma of 0 is equal to x0, y1. Sigma of 1 is equal to x0, y2. What is L of sigma? This is equal to x prime t square. So f of xy, g of xy, both is 1 by y, right? So 1 by y of t square, x prime t square plus y prime t square, and then you want to, this is equal to ds square. So you want to integrate from 0 to 1 the square root of this whole thing times dt, right? In Euclidean case, you would have just taken this, but now you have to divide out by this. Now, this guy is always positive, so this is always going to be greater than equal to, reduce x prime t to 0. So what does that become? This is integral 0 to 1 y prime t by y of t dt. What's that? That's log of y of t integrated from 0 to 1. So this is log of mod y2 by y1. But what is this? X prime t with equality if and only if x prime t is identically 0, right? So anything where there is where x prime t has non-zero values somewhere will have length greater. But what does x prime t identically equal to 0 mean? It means that the x coordinate is constant. That means what is the vertical line, right? So therefore, what have we established? We have established that the vertical line from here to here is a geodesic, a distance minimizing path. Not only that, it is the distance minimizing path, because any other path has greater length. So there is a unique guy joining pair of points which minimizes distances. So first axiom of Euclid satisfied, or at least for pairs of points which are above each other. Right? Okay, good. Now from this collection of geodesics, we want to compute new geodesics, right? We want to join any 2 points. So 2 points which don't lie on the same vertical cannot be joined by a vertical line, right? So we would still like to join them by geodesics. So what is a geodesic joining 2 points? To do that, we like to get new isometries. So what are examples of isometries? One simple exercise that you can do is you look at f of xy equal to x plus a comma y. So then you look at d of this one. This is x1 is equal to x plus a. So dx1 is equal to dx. So that shows you that the ds square and ds1 square are both equal. Right? So these guys are these translations in the horizontal direction, they are isometries. So if you had proven this whole thing for a particular vertical, the y-axis for instance, and you translate it around, you're going to get all vertical lines, all of them are going to be geodesics. Good. Now we come to another here. So this was one computation. Now I'll get to the second computation in this talk. And this is actually something that came from Verma, spherical optics, geometric optics. So here's the fact that you look at, again, you have your hyperbolic plane, and this is your y-axis, this is your x-axis, and you look at, say, the same circle centered at 0, 0, radius 1. Okay? And look at the inversion, the spherical inversion. Assume this is a mirror and you invert in that mirror. Yeah? So, here's the thing. Oh, why am I carrying this in my So, what is spherical inversion? There's a picture way of looking at it. Suppose this distance is capital R, then this is 1 by R, and this theta is the same. This is exactly what you get pictorially if you invert in a spherical mirror of radius 1. The theta coordinate remains the same, the radial coordinate becomes reciprocal, 1 by R. So, so that's the next claim. Inversions about semicircles. So basically you can do this about a circle of radius capital R. But for simplicity of computation, we'll do it for radius 1. So there's a nice way, formula for writing this in terms of complex coordinates. So write z equal to x plus I times y. So this is x and this is the imaginary axis. And what happens is that you are sending, so this guy, so Yeah, so so the right coordinate for this is the spherical coordinate, so or the circular coordinates, polar coordinates. And for that, the complex numbers are better suited. But this is just a computational tool, nothing more. So this inversion is an isometry, that is the claim. What was our formula? ds square equal to dx square plus dy square by y square. Yeah? And then the complex conjugate becomes x minus iy. So can you write this in complex coordinates? Indeed, yes. So this is dx plus I dy, dx minus I dy. What is that? It's dz times dz bar. And what is y? Y is z minus z bar by twice I whole square. So y is, so x plus iy minus x plus iy, which is 2iy divided by 2i, y square. So you've now expressed all this in this terms. And what is this inversion? In this setup, it becomes very simple. So that is our f. Z goes to 1 by z bar. R square by z bar if the radius of the circle was r. But there's a certain constant which I keep messing up every time I do this computation, so I'll choose capital R equal to 1. Okay. So if z goes to 1 by z bar, what does dz go to? This goes to minus 1 by z bar square dz bar. What does z bar go to? It goes to 1 by z. So dz bar goes to minus 1 by z square dz. Now you plug it all back. So dz bar by z minus z bar by 2i whole square. This was the ds square on the left side. What does it transform to? Minus 1 by z square dz bar times minus 1 by z square dz divided by 1 by z bar minus 1 by z divided by 2i whole square, which is the same thing as this is z bar at the here, this is z minus z bar. That's what it becomes. This is the multiplication. So what happens? This is minus, this gets cancelled. This z square, z bar square cancels off with this z bar and this z. So this is equal to dz bar by z minus z bar by 2i whole square. Which means the formula is preserved under this inversion. Yes? Good. So that means inversions about semicircles centered at the origin. If you put R square, this is the same computation works out. These guys are isometries. Yeah? But we know that translations in this direction are isometries. You can compose all of this. So actually you can shift this origin. Yeah. Again, I mean, fixing an origin is something that we attribute to the plane. The plane itself does not care which fellow is there. The plane is much more democratic than us. Okay? So it has, its origin could be shifted anywhere on the real line. Yeah? So this translation is what tells you that that all these points are interchangeable. Yeah? So really, it's not, this is a formula because you set up these coordinates. Okay? There's a difference between affine Euclidean geometry and coordinate geometry. Coordinates are something we put in order to get maps, to do computations. Yeah? But the isometries basically is a way of looking at it intrinsically from the point of view of the plane itself. So inversions about semicircles centered anywhere along the real line, because those are things that you can get by translating by isometries, are going to be isometries, right? Using that, now we want to get, so the last thing is that we want to get new geodesics. We know that vertical lines are geodesics. Image of a geodesic under an isometry is another geodesic, right? What have we got? We've got these vertical lines as geodesics. We've got these inversions about semicircles as isometries. So images of vertical lines under inversions about semicircles centered on the real line are going to give us new geodesics. That's the last thing that we want to do. And there's no computation but a simple Euclidean geometry problem. This is our picture. Okay? So, if you have this vertical line and you want to invert it about some semicircle. Yeah. So, let's say, forget this one. So assume, I mean, if you look at the look at a vertical line, one place would be if you invert it about a semicircle centered at its base. Yeah. Then you will get the line back. Yeah. The top will go to the stuff inside, the inside will go to the outside. You won't get a new line. Okay. Then the point of a circle which is good but not as good as the center is the point of tangency. Yeah? The preferred point. Let's try that out. Yeah. Again, we are playing these games, just trying out various things. So you have this semicircle. Take this vertical line here. This is your L. Yeah. This is your sigma, and I want to compute the inversion. So L inverted about this semicircle. Yeah. What is that? That's my question. The answer is, and this is what was known to spherical people working in spherical geometry, it is actually the semicircle centered at half the radius, and of radius equal to, so the radius is equal to half of the original guy, the center is shifted in this direction. Why is that? So in order to prove this, what we have to do, we have to basically prove that this is x, and look at this, not x, this is x. Okay? So this is our sigma, take little x, invert x about the sigma, and you get this new point y. Yeah? So distance, so this is O. So length of OX, this is equal to capital R. Yeah? Given. Want to show, so to show that length of OY is equal to 1 by R. That's what I want to show. Right? Then I will know that that's the inversion. That's the point that I get under inversion. So then the locus of the inversions as we move along this L is going to give us the same semicircle. Right? So now this is a similar triangle thing. Actually what we'll prove is that this is AB. This is A, this is B, this point is C, and there's this point which is D. Right? So the only thing is just draw this here. This is an angle in a semicircle, so that's a right angle. There's a point of tangency, there's a right angle. Yeah? So triangles, give this a name, ABE and AEC are similar. Yeah? The right angle and there is an angle common, so the third angle is also the same. Yeah? So now apply that. So what do you get? The hypotenuse is AE divided by what's the hypotenuse? It's AC. This is equal to angle. This I want to take this side. So point. This angle is equal to this angle. So what's the side opposite this? This is AB. And what's the side opposite this? It's AE. So AE square equal to AB times AC. What is AE? That's capital R. Capital R is the radius. So R square is equal to AB times AC. That's our inversion formula. Yeah. The product of this length with the big length is equal to the square of the radius. Yeah. Which means what? Which means that if you have this vertical line and you invert it about a semicircle which is tangential to its base, then using this little bit of Euclidean geometry, you get that the image is another semicircle which is also centered on the real line, whose radius is half the radius of the semicircle you started off with. Good. Now, have we gotten, so yeah, this is really the upshot of this computation. Length of AB times length of AC is the length of the radius square. I mean, is the radius square. So we've got a whole new bunch of geodesics, semicircles centered at the origin in the real axis. Actually, we have gotten all semicircles centered on the real axis centered on the real axis in the process. Why? Now invert the problem, the reverse engineer. Start off with a semicircle, the semicircle which contains AB. Yeah? Take a semicircle which is double that size, centered it at A, and draw that semicircle. Yeah? Now take this vertical line at the end. Yeah? So this is just turning the logic around. Yeah? And then you know that the semicircle you started off with, the AB semicircle, is the image of this new vertical that you've constructed. Therefore, the semicircle you started off with, this AB semicircle, is a geodesic. Just pure thought now. Yeah? Good. So now what have you proven? You've proven that all semicircles centered on the real line are also geodesics. Correct? And now do you have enough lines to enough paths to join any pair of points? Indeed, yes. Take any pair of points. What do you want to do now? What you want to do is take any pair of points on the upper half plane. What do you want to do? Given any pair of points here, not necessarily, if they are on the same vertical, join them by a straight line, vertical line. If they are not on the same line, what you want to do? You want to have a semicircle centered on the real line which passes through these 2 points. That's simple. Join these 2 points, take the perpendicular bisector in the Euclidean sense, and my points of intersection are always off, so I make that point a little thick. And so that's your new center, and you draw your semicircle. So this semicircle is centered on the real line, passes through both these points. So any 2 points can be joined by a geodesic. But the vertical lines were unique geodesics. So run this isometry machinery once more, and just the logic once more, and you'll see that this semicircle is the unique geodesic joining these 2 points. Right? So we've got all geodesics in this new geometry. Okay? What are they? Vertical lines, A, B, semicircle centered on the real line. So we've got all the bi-infinite lines. Yeah? Euclid's fifth postulate deals with lines. It has nothing to do with circles or angles. Right? So now we can attack the fifth postulate question. Now it's a question, what is the question? Given any line. So now what is the question? So now choose one of these lines. This is our line L. Yeah? And you have a point P outside it. Yeah? How many geodesics are there through P not meeting L? What are geodesics? Semicircle centered on the real line or vertical lines. Yeah? So certainly this guy is there. There is one chap already there, this L prime. Question is, are there any semicircles? Are there semicircles that you can draw passing through P centered on the real line not meeting L? Oh indeed yes. All that you need to do is assume that it passes through. What do I have to do? Yeah, I want it to pass through this. So again do the same thing. Take the perpendicular bisector. So here you look at this guy and this is going to go outside. Right? So for every point between this and the point that you started off with, in this whole interval, for every point you can take that thing, join it to P, take the perpendicular bisector, draw the semicircle. Right? So what does it mean? You have an interval's worth of lines parallel to the first one, all passing through P. And interval is uncountable. Yeah? So it's the most dramatic breakdown of the uniqueness part of the parallel postulate. Yeah? What does it say? So what have we proven actually? So in the hyperbolic plane, vertical straight lines and semicircular arcs with center on the real axis are geodesics. This gives rise to the following. New parallel postulate. Given a geodesic L in H and a point X, okay, so this X has gotten called P here, lying outside L, there exists infinitely many. What is infinite? Uncountably infinite here. Lying on H, passing through X and parallel. Okay, so the uniqueness of X is broken down. What have we proven therefore? That the first 4 axioms of Euclidean geometry are consistent with unique line. They are also consistent with infinitely many lines. These two fellows don't talk to each other. Through a point, a single line passes. Through a point, infinitely many lines pass. Those guys can't talk to each other. Logically, they are contradictory. Yeah, I mean, my assumption is principle of the excluded third. Yeah? But if you can take any of these contradictory guys, put them there, and you'll still have a consistent system of geometry. Okay? In fact, what Riemann did is that you can remove the fifth postulate altogether, throw it out of the window. It's of no use. Basically, if you put it in and modify it in some form, there is no line is also possible. Zero is also possible. Existence can be contradicted. It's called spherical geometry. A little tweaking has to be done, but anyway, still possible. No line is possible. One unique line is possible. Infinitely many lines are possible, and nothing is also possible. What is nothing? Nothing means sometimes there is one, sometimes there is zero, sometimes there are infinitely. Okay? So that means that the fifth postulate has absolutely no special status. You can discover geometries where fifth postulate is weak. Okay, thank you very much. I shortened overshot quite a bit. Yeah.
Say something about hyperbolic triangles.
What about hyperbolic triangle? Oh, I should say one thing. So maybe this is a question I'm asking myself. Why is it called hyperbolic? I mean, that's a question that everybody should ask, right? Why is it called, what on earth does it have to do with hyperbola, right? And actually that came much later. So it does not have anything to do with the hyperbola. It has something to do with the hyperboloid. Yeah? So if you look at, I mean, and this is where it ties up with physics. So if you look at, when Einstein put space and time together, the metric does not remain this positive definite metric which was given here. It becomes ds square equal to dx square plus dy square minus dt square plus dz square, whatever. So if you have this three-dimensional space, two space dimensions, one time dimension, and you have this Minkowski metric ds square equal to dx square plus dy square minus dt square, and you take the unit sphere there. What is the unit sphere? X square plus y square minus t square. Mathematicians do not give any particular special status to time, so x square plus y square minus z square equal to 1, yeah, or maybe minus 1. That's the unit sphere. Yeah. So that's the hyperboloid, right? So you look at the Minkowski metric, restrict it to the hyperboloid. Yeah. You are going to get exactly something isometric to this hyperbolic. So that's why it's called the hyperbolic. In fact, actually, yeah, I think that model using the hyperboloid was used by Klein extensively. So it's called the Klein model also. Yeah, so, okay, so about triangles, what can I say? Some of the angles is strictly less than 180 degrees. And the area of a triangle is equal to pi minus the sum of the triangles.
Different kinds of triangles in this model.
So what do they look like? Okay, I can draw an example. They all look very similar. This is what they look like. You have a semicircle here. Yeah? You have another semicircle here. You have a third semicircle. This is what a triangle looks like.
But also some with vertical lines.
Sure, listen, the thing is vertical and horizontal is again our Euclidean perspective. Yeah, that is, I mean, the hyperbolic geometry does not say that this vertical lines are special. We want to understand hyperbolic geometry in terms of Euclidean geometry, that is why there is a vertical direction and a non-vertical direction. You see, if we were hyperbolic creatures living inside hyperbolic plane, we would not have this choice of something is, I mean, because of gravity, there is a vertical, there is a horizontal. Yeah? I mean, the mathematical axioms do not have anything to do with gravity, right? So if you keep, I mean, if this board was tilted and there were no ends, where is the horizontal line? So there is no, I mean, there is nothing special here. So if you had this one, you will have this. This is an example. You take an isometry and this, you can flip it over and make it put it there. So this triangle and this triangle may be isometric.
Does Euclidean geometry then come as a special case of hyperbolic?
No, it doesn't. I mean, it can't, right? So because there are infinitely many lines here and there's one and only one line there. What happens is that there is a certain sense in which you can take a limiting case of hyperbolic geometry. What do you do? Basically, I had written this metric here, right? ds square equal to dx square plus dy square by y square. Yeah? You start blowing up this metric. So you start multiplying this by, say, epsilon n. So what does it mean? You are passing more and more. So I mean distances which were, hang on, I'm doing it the right way. I should scale the metric, yeah. So this, say n square, yeah, just capital N square, where capital N is just the natural number n. Let n tend to infinity. Yeah. What is happening is that, so there is a notion of curvature. Yeah. So the sum of the angles of the triangle here, if you take the largest, yeah. Okay. So there is a, what is happening is that this triangle, which was of a certain diameter in the original hyperbolic plane, in this guy, is going to have diameter n times that. So which means what, the whole space is running away from you if you choose to be at a particular base point. In the limit, you will be standing on the Euclidean. So in that particular sense, the Euclidean plane is a limit of the hyperbolic. It's also the limit of spherical.
What happens with the notion of angle and
Oh, the notion of angle is okay. So yeah, there's so what is angle? I mean, angle is if you want to look at an angle, so you can compute. I mean, in physics we compute angles between tangent directions, right? So what are we really doing? We are taking a point. We are looking at tangents to that. The collection of tangents actually forms a Euclidean space. Then we can do our product, compute the angles, all that stuff. So what is going to happen? You take this point of intersection, you take this tangent direction, this tangent direction, and compute the angle between them in the normal Euclidean sense. Yeah? That will turn out to be exactly the angle in the hyperbolic metric also. Why? Because, see, basically if you take two lines to a point and you scale, the angle between them does not change, right? So this is called a conformal change. Basically every point, the x direction and the y direction are being multiplied by the same number. Look at this function. This y is scaling both the dx direction and the dy direction by the same amount. So conformally, in terms of angles, the angle in the hyperbolic plane and the angle in the Euclidean plane are not. So the notion of angle certainly makes sense. And through every point, I mean, yeah, all right angles are right angles. I mean, they're all equal to each other. That's axiom also. Yeah. Yeah, go ahead.
Why did we restrict the plane to only y positive?
That is what here from the formula it's very simple. Y goes to 0, you can't have that, right? If y is going to 0, right, that metric is blowing up. So there is a singularity.
So you can keep that off and take negative.
Then there are two pieces. Then you will be doing geometry on the top, geometry at the bottom in a parallel universe. And the two will not communicate. Huh? Yeah, so there is no geodesic that goes from the top guy to the bottom guy. Yeah. No, that is not an accurate statement. So, yeah. Then you will get the same geometry on the other side. Flip it.
Yeah. My question is, like in the last slide, like you have mentioned that all the geodesics are, you mentioned the bifinite geodesics.
By infinite, yeah.
By infinite geodesics.
Yeah.
But I can understand a vertical geodesic being infinite, but a semicircular geodesic.
Why is it by infinite? Very good question.
Yeah.
Very good question. So you can imagine that the vertical line is infinite. Why? Because it is going off. See, this is an example of, again, our Euclidean schooling. This is going off to infinity in the top direction. Where is it going in the bottom direction? Compute the length there. Log of, say, you start off at the point 1. Yeah? And you start going, you take your point going off to 0. What is the length? Log of 1 by epsilon. That length is going off to infinity. Right? And now what has happened here with the semicircle is that the semicircle is a much better fellow than the real line. Why? Because it treats this step and this step equally. They are both going off to infinity and they are not looking as if they are going off to infinity. Okay?
So I have another question, like how does this look like if I project it into another dimension, like imagining that.
So yeah, so there is a hyperbolic free space. All that you need to do is put dx square plus dy square plus dz square. Yeah? And then you do then x, y, z is a restriction of the human alphabet. You put x1, x2, xn. That's n-dimensional hyperbolic space divided by xn square.
Is there some way to visualize it, like?
Sure. There's somebody called Bill Thurston, who is a mathematician, who actually, after Poincaré, there's a new person who sort of brought it back in this very tactile geometric way by which you can manipulate. So it's been done. I mean, the field has actually reached, in some sense, I mean, all the major problems got resolved over the last 4 or 5 years. Just, yeah. So now,
Thank you.
yeah, 3-dimensional. That's only in dimension 3. I think we are still waiting for a 4-dimensional thruster. Yeah. So we don't have. I mean, the problems are very different. Yeah. Okay. So 3-dimensional. Have you heard of somebody called Grisha Perelman, for instance? Okay. So this is a mathematician called Grisha Perelman who won the Fields Medal but refused it, and he was offered $1 million prize, refused it because he's a mathematician. So, and that's the shortest and dishonest way of saying it. But yeah, so he solved perhaps. I basically said that you take a generic 3-dimensional structure, they're called 3 manifolds. It has a hyperbolic structure. Yeah? So with probability 1, the universe we live in is hyperbolic, not Euclidean. So if there is no other extra assumption, then yeah, go ahead.
So suppose we bring this hyperbolic plane into the Euclidean 3D space.
Theorem by Hilbert, it cannot be done.
It cannot be done. No, like suppose
not in 3-dimensional space it can't be done. Certainly can't be done in 2-dimensional space. Theorem by Hilbert says that you cannot take a complete hyperbolic object and embed it in 3-dimensional flat Euclidean space. Theorem from 1901.
And suppose the number of parallel lines is reduced to 0, then can that...
How do you
not a hyperbolic plane. Like suppose from geometry we manipulate stuff.
What do you mean? No, don't be vague there. Yeah? I mean, you're shoving again. The whole point was don't shove anything under the carpet. What do you mean by reducing number of lines to 0?
Suppose
pick them out one by one. What do you mean? Mathematically, what do you mean?
Suppose there is a line and we have a point.
Yeah.
There is no such line through that point which is parallel to this line.
Are you imposing this as an axiom?
No, we want a plane which holds this property. Like
yeah, so okay, there we want it. So basically what you're saying is, what is an example of a geometry where the number infinitely many, number 1 is replaced by 0? Is that your question?
No, I want to say that can that type of plane be brought into a 3D space?
Yeah. The example is the sphere.
Okay. But this cannot be brought.
No, this is a theorem of Hilbert that it cannot. In fact, actually all planes follow great circle routes. Right? Why? Because the great circles are the shortest planes. And 2 great circles certainly meet at 2 points. Yeah? So they meet at 2 points, not 1 point. But it's certainly true that given any great circle, given a point outside the great circle, there is no great circle through that point which does not intersect the first great circle. Okay? Yeah.
Kind of like a primary question.
Yeah.
In the second theorem, you proved that all vertical lines and semicircles centered on the
real axis
are
yeah, straight lines.
Yeah, they are isometries. So
they are not isometries; they are geodesics.
Sorry, they are geodesics.
Yeah,
sorry, in the second theorem, you proved that all inversions using such semicircles are geodesics.
All inversions are isometries.
Sorry, isometries.
Yeah. So isometries, think this way. These are your objects, straight lines.
Yes.
And these are your maps, isometries. Okay? So objects get mapped to other objects. What goes in between them is the relation. That's the function. Yeah. Okay.
So my question is, your second theorem was that all translations and all inversions using such semicircles are isometries.
Correct.
Then that doesn't, how will you prove the converse? That any general isometry...
I did not say the converse. The converse is false. Any statement does not have necessarily mean that the converse has to be true.
Okay, so...
What is true? I'll tell you what is true. Any isometry can be described as a composition of 3 of these inversions.
3?
At most 3. This is another fact. It's also a nice thing. You can work it out. All it involves is Euclidean geometry, not even hyperbolic geometry. So, have you heard of Mobius transformation? Z goes to Az plus b by cz plus d. Yeah. So, what are the composition of 2 of these inversions are going to give you Z going to Az plus b by cz plus d, where a, b, c, d are real. Yeah. And modulo this one reflection in the plane. So, if you are given a line and you say that the 2 sides are preserved, then the set of isometries of the hyperbolic plane are precisely equal to the set of Mobius transformations. And place of the Mobius transformations is really the context from which that metric comes up. Okay? So the motivation for picking that metric out of this uncountable hat is basically because Poincaré was looking at solutions to differential equations in complex numbers, complex analytic types. Yeah? And so he was trying to find complex analytic transformations that preserve various structures. And he found, apparently when he was getting onto a bus, that the hyperbolic isometries or this hyperbolic geometry that he was thinking of and this complex analytical stuff that was coming from differential equations, they were the same thing.
Okay. Let's thank Professor Mahan for a wonderful lecture. We are running a bit behind the schedule, so we'll take a 15